Hello, ladies and gentlemen. This is Mr. Hunter, and this is your Wave Notes Part 1. So, this is our fifth unit, and so we are going to talk about the basic characteristics of waves, and then we are going to go into the different types of waves and learn more about them and their characteristics as well. So, to start off, in class, I had a pendulum, which is my chain hanging on the bowling ball, and I pushed it and let it swing back and forth. And as a result, this is called simple harmonic motion. And simple harmonic motion was a motion that repeats itself constantly. In particular, if it's perfect, it continues in the same time period of getting back and forth. And you've seen this with like grandfather clocks and other items that use a pendulum. So what simple harmonic motion is, it's motion that repeats itself, and it's where the restoring force equals the distance moved. So depending on how much I pulled it back, it would swing to the other end, and if there's no friction, it would swing to the exact same point because of conservation of energy and come back. Now, in this case, the restoring force is gravity. If I were to do simple harmonic motion with the spring, the restoring force would be the spring itself through Hooke's law. So the restoring force equals the distance moved. And so as a result in class, and this should hopefully be review at this point, is we mapped or graphed the motion over the angle that it traveled. So for example, when I held it back, we said, okay, it has an amplitude of 1. And then once it gets to the bottom of its swing, that's amplitude 0. And then finally, if it gets to the other side, it's an amplitude of -1. And we took those data points, and as you can see, we made a wave. In this case, it's a cosine wave, but I could shift it 90 degrees over, and it would become a sine wave. So, or actually, yep, shift it over 90 degrees to become a sine wave. So, as you can see, this has a certain length, which we call wavelength, and there's parts of the wave that I'm going to teach you about now. So, because it's really important that you know about the different parts of the wave. So, the first thing is a wave is a transfer of energy, typically in a given direction. And we're going to learn in a little bit that there's two types of waves that have this transfer of energy. And so we have the crest of the wave, which is actually the very top of the wave, and then we have the trough of the wave, which is the very bottom part of the wave. And then we have what is called then the wavelength. Now, this green symbol that we use is called, it's the Greek letter lambda, and it means wavelength. So remember, the units of lambda would be meters, and that little squiggly sign with the leg, that it represents lambda. The lambda, or the wavelength, is one complete cycle. So in this case, when it starts at 1, and when it gets back to 1, that's one whole wavelength. Now, a sine wave is a little different because it actually gets back to its starting point and then returns there. So for a sine wave, it actually completes one whole cycle, which is it goes from 0 to up, down, and around. I'll show you the picture in class. So then we have something called the frequency. Now, the frequency is a number of cycles in a given period. So if you were to say the frequency of this wave, what it really means is you have a bunch of wavelengths in a certain amount of time. So for example, if you remember the merry-go-rounds that you had in your elementary school or at a playground, and so let's say that you're on the inside, and let's say that I was able to spin that around really fast. So let's say I was able to spin it around 10 times in 10 seconds. This actually is going pretty fast. The frequency would be the number of cycles per unit of time. So the frequency would be 1 hertz. Why? Because I went around 10 times in 10 seconds. So in about a second, I've made one complete revolution. So that's the frequency, which is the number of cycles in a given period of time. Case in point, if I push that pendulum back and forth, its frequency would be how quickly it gets back in a certain amount of time and how many cycles. So let's say I pushed it really fast, and so in 1 second it completed 5 whole revolutions. Well, the frequency would be 5 hertz because it did 5 seconds, which that's the unit for frequency. The unit is called the hertz, the hertz, and what it really means is 1 over seconds, or seconds to the -1 if you guys remember your math terms. So the next thing that I want to talk to you about is period. The period is the time it takes to complete one cycle. So so if it goes back and forth and I time it, that's the period of that simple harmonic motion. Or in the case, the period would be 1 second, or in the case of the merry-go-round. It's the time it takes to complete one cycle. And the equation for that is, I'm going to actually write this up on the top, but the equation for that is T equals 1 over frequency. In the same way, frequency, if we cross multiply, is just 1 over period. They're related to each other. So frequency and period are related to each other, and that's how you find them. So period would measure in seconds because it's time, and frequency would measure in hertz, which would be 1 over seconds. Okay, so then lastly, we have the amplitude. The amplitude is how tall the wave is, and we measure it from 0 to maximum height. So in this case, this wave that we drew has an amplitude of 1. We don't take it from -1 to 1. We only measure from 0 to its maximum value, and that's the amplitude of the wave. Now, here's the interesting thing is, the amplitude of the wave actually is able to tell us how much energy the wave has. Because think about it. If I were to yell louder, that would increase the amplitude of my wave or the height of my sound wave. If a light gets brighter, that would increase the amplitude of that wave because it's getting brighter. So amplitude is really how much energy the wave has, and increases or decreases, and that tells you, like, if I were to speak softer, I decrease the amplitude of my wave. Or if I speak louder, I increase the amplitude of my sound wave. Now, that's the basic thing about waves. There are 2 types of waves that we deal with. One is called longitudinal, and I demonstrated in class what this is. And this is matter moves parallel to the energy. So when I took the spring and I pulled it back, you notice that the energy, which was going towards the other student that was holding it, is parallel to the material. So the material's moving left and right, and so is the energy. And so a picture of this, I tried to draw it the best I could, was here's the spring, and I pulled it back. So the energy is going left and right, and so is the material. So longitudinal, the energy goes left to right, and so does the material, aka parallel to the energy. A sound wave is a longitudinal wave. Sound wave is longitudinal. Why? Because when I speak, my vocal cords vibrate, which vibrates the air molecules in front of it, which push the air molecules in front of it, pushes the air molecules in front of it until it gets to your ear. And if you look on your reference table, the speed of sound in air at standard atmospheric pressure is 331 meters per second, which means it gets to your ear with that speed at standard pressure. So even when I'm talking to you right now, sound is moving at 331 meters per second. Now, the other type of wave is called a transverse wave. And this is where matter moves perpendicular to the energy. So this was when I sent like a pulse of energy towards the other student. The energy is still traveling to the student. However, the matter or the material is moving up and down. So the matter moves perpendicular to the energy. So that's where you actually can see what the wave looks like. Longitudinal waves are harder to actually see. You see compressions and you see extensions, whereas in transverse waves, you actually see the matter moving up and down or perpendicular to the energy. Like, we don't really see the energy that's traveling. We really see the matter that the energy is traveling through. Now, a type of transverse wave is a light wave. A light wave is a transverse wave. So the energy is moving still left to right, but the matter is moving perpendicular to it. Now, I just also wanted to define what a pulse was, because like it's really just sending one little shot or beat of energy towards the other person. Because when I start sending multiple pulses, that's what makes the simple harmonic motion, or that's what makes appears to be a standing wave because I'm sending multiple pulses of energy down towards the other student, and they're interfering with each other, which means adding and subtracting. And that can make either a standing wave, or it just makes different types of waves when they add and subtract. So I'm going to stop there for right now, and I will collect this when it is due. Have a good day, ladies and gentlemen.